So in this second short video, we're going to talk about partial derivatives and maximizing a function that is a function of multiple variables. So before I do that, let me just review what we had just talked about. So when we were trying to maximize a function of one variable, the way we illustrated that graphically is that we had that the thing that we're trying to maximize or minimize is in the vertical dimension. So let's say we're trying to get something that's as high up as possible on this graph here. And we did that by sort of moving left or right along this horizontal dimension. That's sort of the one dimension that represents the input to the function. Now, to start looking at more dimensions, let's say we have a function of two variables. We're going to need to add a third dimension. So I want you to imagine the dimensions as so. So we're still going to be trying to maximize the vertical dimension. But now we're going to have two input dimensions. One, which we'll call x, that moves sort of horizontally, just like in that last example. And then we're going to have another input dimension, we'll call it y, which moves straight towards you. So it moves along this direction. Okay? And the thing that we're trying to maximize, the height of this, we'll call that the z dimension. Okay? So sort of you can imagine that the function looks something like this mini soccer ball. Okay? You could sort of move along the function along the y dimension, which is sort of towards you, or along the x dimension, which is sort of horizontally along this axis here, this way. Right? Okay, so keep on imagining that that three-dimensional graph with the y dimension, the x dimension, and the thing you're trying to maximize, the z dimension. And with this ball here, trying to find the highest point, you have to think about what would be the necessary conditions for a point on this ball to be the highest point, the maximum point. Well, when we were looking at just one dimension, the necessary condition was that the slope as you move along this horizontal dimension would be equal to 0. The necessary conditions when you have these three-dimensional graph with two input dimensions is that the slope has to be 0 moving along each direction individually. So if you're just moving horizontally, it has to have a slope of 0. If it didn't, let's say that you're at this point here, then moving further along the horizontal dimension to the right would raise the value, would yield a higher value on the function. Okay, so if we want a point to be the maximum, it has to have a slope equal to 0. Otherwise, it is not the highest point. Similarly, if you look at this point here, the slope at this point, I don't know if you can see it, is not 0 along the y dimension, which suggests that if you move closer to me, further from you, you would get to a higher point. So another necessary condition is that the slope along this y dimension also has to be 0. Okay, so you have sort of two necessary conditions. The slope along this dimension is 0, and the slope along this dimension is 0. Okay, so that's the basic idea here. We're not going to worry about the second order conditions to make sure that what we found is a maximum or a minimum. We're just going to focus on those necessary conditions. Okay, so now let's think about what that means using calculus. Well, to get the slope along one of the dimensions, what we're going to do is we're going to use the partial derivative. Okay, that basically means if you're moving just along one of the dimensions, what is the slope? And the way you calculate the partial derivative is you take the derivative with respect to the variable that you're looking at. So if you're moving along the y direction, it's the partial derivative with respect to y. And when you're taking that partial derivative, what you do is you keep the other variable as if it were as constant. Like you treat that variable just like you would a constant. Okay, so I can give an example here. So let's say that the function you're trying to maximize is z is equal to x plus 2y plus x times y. And let's say that we're taking the partial derivative of z with respect to y. Okay, now let's do that. So we're taking the partial derivative. We have three terms added together. We're going to take the partial derivative of each and add them together. So let's look at this first term here. It's just equal to x. Now, as I said, when we're taking the partial derivative with respect to y, anytime you see an x, you treat that exactly as you would a constant, like exactly as you would the number 5. Well, if you were to take the derivative of just the number 5 with respect to x, partial derivative of 5 with respect to y, what would that be? The derivative of just a number is 0. Right? If you took the derivative of 5, it's just equal to 0. So when we're taking the partial derivative of z with respect to y, the partial derivative of this first part, which is just going to be equal to 0. Right? So kind of draw that. Okay, now let's take the partial derivative of the second part with respect to y. Okay, so the second part is equal to 2y. The derivative of 2y with respect to y is simply 2. And now let's look at this third term, and this is what tends to lead to the most confusion. Okay? When you're taking the partial derivative with respect to y, you're going to treat x just like a constant. So if this last part were not xy, but were 5y, what would be the derivative? It would just be 5. Okay? But it's not, this last part is not 5y, it's x times y. But we're going to treat x exactly like we would a constant. So when we take the partial derivative of this last part with respect to y, the partial derivative is simply x. Okay, so the partial derivative of this entire function with respect to y is 2 plus x. Okay? So it takes a little bit of time to wrap your head around it for those of you who have not taken Math 10b, which is the class that goes over partial derivatives, but is not a prerequisite for this course. For those of you who have not taken Math 10b, you will have to sort of spend a little bit of time getting used to this. But there aren't any new rules. The key thing to keep in mind is just that when you're taking the partial derivative, let's say with respect to y, you treat the other input variable x exactly like you would a constant. Okay? And so then what we're going to do is, to solve the problem, we're going to have some function, let's say, that we're trying to maximize. We're going to take the partial derivative with respect to one of the variables. So, let me just clear everything and I'll show you exactly what I mean. Okay, so let's say you're trying to maximize z is some function of x and y. Okay, so to do that, you're going to take two partial derivatives. First equation is going to be that the partial derivative of this function of x and y with respect to x is equal to 0. So you take the partial derivative of x, whatever that equation is, you'd set equal to 0. And then you do the same thing, but taking the partial derivative with respect to y. Setting that partial derivative equal to 0. And then you would search for the values of x and y, which make it so that both of these two equations are equal to 0. So that's how you'd go about solving the problem. Now, I want to clarify one common misconception. Oftentimes, one thing that's misunderstood is that for you to use this method, the two input variables, in this example x and y, have to be two different variables that you are free to choose between. So for example, if you're looking at the firm's problem where they're trying to choose the price and advertising level to maximize profits, price and advertising are two different variables that you could set to any level. That one does not depend on the other. And so it would make sense to use a method like this. Where it would not make sense is where those two variables are not really independent from each other. So for example, if you were trying to maximize a monopolist's profits and you try to choose a value of price and quantity to maximize the profits, you would set the price to infinity and the quantity to infinity. Okay, but that doesn't really make any sense, right? Because the price determines what quantity the monopolist can sell. They are not really two different variables. And so you wouldn't want to use partial derivatives because you can't just freely set each one. It wouldn't really make sense to do that. So in that case, there's another way you could solve it, but I'm not going to spend time thinking about or going over that now. Okay. So let's get back to partial derivatives. I have a few more practice problems that I'm going to quickly go through here. Practice partial derivatives. And then a couple of practice problems where you're trying to find the maximum or a minimum of a function. Okay, so now let's practice taking a couple partial derivatives. So let's consider function f of x and y, and let's say it's equal to x plus y. And now what I want you to do is to find the partial derivative of x plus y with respect to x. Okay, so you can pause the video, try to work on that for a minute, and then when you're done, unpause the video and you can verify your answer or see the solution steps. Okay, so when two things are added together and you take the derivative is just the derivative of those two things added together. So let's first take the derivative of this first part, x, with respect to x. That's just equal to 1. And now let's add to that the partial derivative of y with respect to x. Again, we're going to treat y exactly like a constant, like we would the number 5. And take the partial derivative of a constant with respect to x, it's just equal to 0. So the partial derivative of this first function is just equal to 1. Now let's try the second function where f of x and y are equal to 2 times x times y. Okay. So we want to take the partial derivative of that function. Okay, so let's take the partial derivative of 2 times x times y with respect to x. Pause the video, think about it for a second. When you're done, unpause. Okay, so to help clarify this, let's break this into two parts. Let's break this into the part which is equal to the constant, which is then multiplied by x. So if we rearrange by bringing this y forward, now this 2 times x times y is the same thing as 2 times y times x. Where this blue part here is going to be treated as a constant when we're taking the partial derivative with respect to x. Okay, so if you have some constant times x, the derivative is just equal to that constant. Where here, the constant is 2 times y, where y is the other variable that we are not taking the partial derivative with respect to. Okay, so that's the first type of problem we're going to quickly go over. Now we're going to try and go over finding the maximum, or finding the values of, well actually it's going to be the minimum. Find the values of x and y which minimize the following function. So we're going to want to minimize 2x squared minus x plus y squared minus y. And the way we're going to do that is we're going to take the two partial derivatives. We're first going to take the partial derivative. Let's call this whole function here z. Take the partial derivative of z with respect to x, and that's going to be equal to 4x minus 1. And we set that equal to 0. And now we're going to take the partial derivative with respect to y, which is equal to 2y minus 1. and we set that partial derivative equal to 0. And then we're going to find the values of x and y, which make it so both of these equations hold. So you can see pretty quickly that the solution is x is equal to 1 over 4, and y is equal to 1/2. So this is what the necessary conditions tell us. We're not going to worry about the second order conditions. So this would be our solution. So this was actually a simpler example. We can sort of go through these steps to solve it. In a lot of cases, you'll actually have that each of the partial derivatives will depend on both variables. Here, the partial derivative with respect to x only depends on x. So we can solve it just looking at that one equation. And the same is true for the partial derivative with respect to y. It only depends on one variable, y. In a lot of other problems, you may have x and y in both of these equations. And you just have to find the values of x and y which satisfy both. There's a variety of methods you could use. You could solve this first equation, let's say for x. You plug that in for x in the second equation, so and you could then have the second equation in terms of only one variable. There's a variety of different methods. You can kind of review that. We'll be using those methods a lot in this class. It's worth quickly reviewing. But that's basically it. That's how you would solve for the values of x and y, which in this case minimize this function. It's similar steps to maximizing a function. And as I said, I know that partial derivatives are not something that many of you have seen before, because taking a class with partial derivatives is not required before you take my course. However, once you get your head around it, it's just basically applying all the same rules for derivatives, but just keep treating the other variable that you're not taking the partial derivative with respect to, just treating that one as a constant. So that's really all it is. You just have to practice it a little bit.